Welcome to the AATRN Topological Complexity Seminar. Our speaker today is Dan Guralnik from the University of Florida, who apparently is recruiting. Take it away, Dan.
Thank you very much, Dan. I would like to thank the organizers and especially Dan Cohen for this opportunity to talk. And yeah, I'm sort of recruiting. I think this field needs a lot of help. I will probably only cover about half of what I wanted to talk about today. So I will not cover ideas about learning, which I was supposed to talk to you about 3 years ago when you had a workshop conference in Gainesville. Actually, my son was sick then and I missed it. Okay, so let's start. So the title is intentionally ambiguous. It's both topologists that are wanted perhaps by the autonomous robots community of researchers, but also every autonomous robots community. I would like to make that point. Every community of autonomous robots would like to have a topologist thinking for it. And I'm going to talk about examples from my work that look in this direction. Oh, just a second. Okay. So is there a way for me, I'm sorry, to somehow move the Zoom banner from the top to someplace else? Do you know? I guess I will survive. So
if you click on view, you might be able to reshuffle a little bit, but I don't know.
Like I'll stay with this and see how we go. So yes, so I would like to sort of start, especially for the benefit of the people I invited to join this talk, and who don't know exactly what TC is. I will not say exactly what TC is, but I would like to sort of comment on where topological complexity of a space comes into the discussion comes into robotics. And so the different flavors of topological complexity, as far as I can understand, could be really seen as useful homotopy invariants, which quantify the complexity initially of path planning, where given an initial state and target state, you would like to find a path joining them, but with the paths to the extent possible varying continuously with the endpoints. And so topological complexity essentially quantifies, in some sense, what is the minimum number of discontinuities that you're going to encounter in trying to achieve this task. But over the years, additional, more general tasks were considered, and TC variants were constructed for those by the people present, by the people running this seminar, essentially. And so we can talk about path planning with a prescribed number of stops that is higher TC. Path planning taking account of symmetries, so we can talk about equivariant topological complexity. And most recently, path planning in a parametric family of environments, allowing the construction of, so to speak, piecewise continuous path planners that take into account the possibility that perhaps obstacles in your environment might move. So overall, TC comes from a foundational problem in robotics, which is the problem of planning motion, planning paths for a mechanical system through an obstructed environment. And you might be thinking of some multi-jointed arm kind of robot trying to move its end effector, grab something, move that something elsewhere, while avoiding stationary obstacles that sit in that environment. However, the problem is there is a little bit of a disconnect between the robotics community today and this problem. The robotics community has moved along, and now I guess I'm allowed to say we are studying autonomy, and I would like to talk about what that means, because the truth is that autonomous robots and AI-based systems are already impacting the world, right? And I sort of wanted this to feel a little bit ominous, because we don't have many guarantees of how these systems behave, especially the artificially intelligent ones. So perhaps most important here for a mathematician is sort of to try to understand what is the difference between autonomous and non-autonomous robots. And the murky pond in which we can actually fish, and I think there are many fish in this pond, is that there is not an answer. We just sort of understand that the complexity of the task and the required degree of supervision delineate the boundary, the very fuzzy boundary between autonomous and non-autonomous. And so to see this, let's talk a little bit about what the original control paradigm was historically. So the general formulation could be roughly seen in this way. So you have a robot, some mechanical system perhaps, and it has dynamics in some high dimensional space. So x dot is f of xu, f is probably a complicated function and nonlinear one. And given an initial state x naught and a reference trajectory, a desired motion that we would like to execute, in spite of the dynamics, we would like to find a control input, so u of xt, which will stabilize the deviation or the error, right? The deviation of the actual state of the system over time from the prescribed state. And we would like a stability guarantee that's as strong as possible, of course. And so let's talk a little bit about where autonomy comes in. The dynamical system may not be known. The function f may not be known. We perhaps understand how the control might affect f a little bit better than we understand how the state affects f. We may not even understand the state itself with great precision because the state may not be measurable. And so properties of f, if you have some bounds on components of f, so to speak, say when f is a control-affine function of the state, for example. So bounds may be used to overcome undesirable behavior. And so essentially you crank up the control input so hard that desirable behavior occurs simply because you drown out the dynamics f. And this is the robust control paradigm, which results in highly conservative controllers, which often cannot be realized on actual mechanical systems because, as Dan Kodicek always says, it's hard to crank out the joules, and so especially with electric motors. And so another option is for us is to collect data, estimate the state, and try to improve that estimate by collecting data over time. And this is the adaptive control paradigm. And the problem with that is that often you get to approximate, you think you're going to approximate f, but you end up approximating, well, something else, though you still are able to control the error. And another characteristic of adaptive control is that sometimes controllers will have to be discontinuous. And so autonomy here is about really overcoming the lack of precise model or state knowledge for the purpose of following a virtual leader. This is a local kind of autonomy. And what you notice is that this kind of autonomy, the ability to reject unexpected disturbances, for example, it's very important, but still someone had to provide you with the desired path to follow, which is why we need continuous or piecewise continuous planners. This is where the problem, right? The problem that motivated topological complexity I hope I'm right, in Michael Farber's mind, this is where the problem came to be. And so being sort of dissatisfied today with local autonomy, or to be more precise, essentially saying there is a lot that local autonomy can give, but there is something it cannot. It cannot tell us what to do. It can sort of just tell us how to do it. We need to think about how global autonomy arises. What is that? And so the first aspect of global autonomy that's been developed over the past, well, quite a few years, 2-3 decades already, is how to deal with task constraints and specifications. And you can talk about domain invariance under closed loop dynamics. And you can talk about desired limiting behaviors. So domain invariance is really about, say, avoiding obstacles. It's about safety. Whereas desired limiting behaviors, that's about the goal. Right? You might want a stable limit point for your trajectories. You might want a stable limit cycle or a limit manifold of some sort. And so what came to sort of begin to realize the notions of global autonomy was the reactive paradigm. So instead of planning, you try to construct global solutions which can be computed locally. So for example, navigation functions, Morse functions on the state space that have only one minimum and otherwise have saddles only, have only saddles, are this sort of artificial potential for which, if you do gradient descent, you can reach a target point from almost all initial positions. And so think about, instead of planning, you create reference vector fields with known attractors, limiting dynamics, and robust, almost everywhere stability properties. And these almost everywhere stability properties are almost everywhere because obstacles will impose topological constraints that will force your vector fields to be null in places that are not your target or your target manifold. And so local autonomy is helpful here. It is going to be used, its capabilities are going to be used to track the reference field. And then the next step is to create long-term behaviors by covering the state space with subdomains that have these reference vector fields, or navigation fields, if you like to call them this way, and then sequentially compose these vector fields according to a higher level plan, basically moving from subdomain to subdomain in order to execute your task. And so this creates this graph that was called in the literature the prepares graph, also a Kodichek and Ritzi, I think, contribution that allows you, that's searching through which will allow you to reach your goal, reach your destination in the long term. And so it turns out there's, of course, a price to pay when you switch from a planning paradigm to a reactive paradigm, and that is that you cannot plan, you cannot look for best paths by default. And so there are some trade-offs that you can observe in different examples. I've put in as an example a work I did with Dan and his student. There are some trade-offs between optimality of behavior For example, when moving n particles in RD without collisions, and the computational cost of navigating the high-level structure. And the high-level structure there was inspired by clustering ideas. And so let's try to move on to a little bit of math, and let me try to give a sketch of an approach to dealing with high-level abstractions, which is more or less state of the art. And having given that sketch, I will try to offer an alternate variant of realizing that sketch that is mindful of the topological properties of the problem. And so try thinking about a situation where you have a state space X, sort of Rn minus obstacles would be a standard example. And this X would be subdivided as the union of disjoint cells that are sufficiently nice. Usually people would like those cells to be convex. Which in the case of complicated obstacles means a very large subdivision with lots and lots of cells. And so let's keep that in mind. And so possibly if you, sometimes the important cells, so to speak, are very far from each other. And so you'd subdivide the space into a disjoint union of closed cells, and then they will have a common connected complement. And suppose that you have already low-level controllers, and that's why you want the cells to be nice. You have low-level controllers that realize your local autonomy to guarantee transitions between these regions, between these cells that I also call atoms. So in the case of there being a common connected complement to the atoms, you sort of get this starfish discretization of X, where every atom is connected to the complement of all the atoms. And this is a very useful setup in which usually this temporal logic-based constraint framework will work. And so the atoms form an alphabet for generating Boolean observations of the system state, right? I basically at every state I can ask, am I contained in one of the atoms? Or am I on the common boundary of two atoms, etc. Notice that I'm using the words disjoint, subdivision very loosely. And so if I'm somewhere, right, if I'm at a particular point in the space, I can ask the question, am I contained in an atom? And the answers are going to be yes or no. And there is a corresponding Boolean observation or Boolean statement that I can write down, which will be true at that point. So a discretized presentation, X prime of X, essentially is constructed by taking the possible 2 to the atoms states and connecting them with directed edges labeled by the controllers that can provide the transition between such state, between these abstracted discretized states. And once you have that, you can say, okay, given a task specification, which is a formula phi, I'm deliberately vague here because there are different temporal logics that could be used for these purposes and slightly different variations of this framework. So you think about a formula that says start in A, then move to C without hitting B and D, and eventually end up in E without returning to C. Stay in E forever. So a formula like this is a much richer task specification, potentially, than just asking for a path that brings us from A to B. And so let's have this as our standard of high-level abstraction and high-level specification. So a formula like this, it turns out, has a finite state automaton that accepts precisely the infinite words over the state of chunks of a set of chunks of x 2 to the AP, which satisfy phi. And so what you do is you say, well, to create a plan that satisfies phi, all I need to do is create directed paths in the product transition system x prime with the transition system defined by the automaton, which project to an accepting state of the automaton infinitely often. And the reason is that a word is accepted by our automaton if and only if it hits an accepting state infinitely often. And so this is a paradigm. This is a paradigm that's being used currently, and in a sense is a state of the art. Again, with different corrections for different kinds of temporal logic. And so the challenge really is that these automata grow exponentially with the size of the formula. And the question is, can topology help? Can topology help inform and expand this method? Even just understanding whether the formula phi could ever be satisfied by the transition system, by the discretized presentation, is not a trivial matter. And that is why to lower complexities, people prefer to work with a starfish discretization of x, because that means the discretization is very simple. And otherwise prefer to work with decompositions into convex cells, because at least then the local autonomy part is not that hard to instantiate. But still, this results in very large transition systems that just simply have to be searched for paths that are good enough for us. And so again, the question is, can topology help? So let's see if it can. Well, I don't know the answer. In some sense, this is an ongoing project with Yu Wang, who is also on this call right now. Let's have some simple observations. Let's make some simple observations. So as I mentioned, the geometry of atoms is very restrictive. And so instead, you could imagine that an atom, we should be able to take atoms that are just contractible, or more generally navigable. We know that just from an understanding that reality is never piecewise linear. In reality, it's very hard to take a problem and subdivide its state space into convex polyhedra. And so with such general / generic atoms, well, why not let the atoms cover the space X? And perhaps we should even take advantage, if we can construct a good cover in the sense of satisfying the conditions for the nerve lemma, that should be helpful. We would have the nerve as a homotopy model of the space X to begin with. And so if we have a good cover indexed by our atomic propositions, so this is a slight change of recipe here. We definitely do not want the atoms to be disjoint. And so if we have a good cover, we take a partition of unity for a second, where every function with the appropriate index is positive exactly on the covering element. And then we get a map from X to the geometric realization of the nerve, which is in the simplex of dimension atomic propositions, of dimension given by the atomic propositions. And so this is standard. And we would like to be using the nerve, perhaps, as a discretization of X encoding topological constraints on a formula phi. And that's because the simplices in the nerve, in fact, correspond to simplices in the nerve correspond to the non-empty intersections, right, of covering elements. And under this realization, when you're thinking about this map, you're only hitting an open simplex corresponding to a particular subset if you are in that subset and you are for any other element of for any other atom that was not mentioned, you are in the complement of that atom. And so we have a feeling that the nerve of U can serve as a discretization X prime. And so plans ought to somehow live in a product, which one would need to construct of the nerve U with the automaton for the formula. But there is a constraint, right? Plans, good plans, so to speak, have to be lifts of paths in X. And so that's how topology of X should be informing the structure of this state of the space X prime. And more importantly, the structure of this product, which is not yet clear what it means. So it's clearly a Cartesian product, but with additional transition structure in it that's not immediately obvious. And there is then a question, what kind of map will this projection back to X going to be? What do we have to require? How weak of a notion do we need? And so we were thinking with you, Wang, about how we're going to match the space to the automaton. And it's important to understand that these automata corresponding to formulae have their transitions labeled by complete terms, by elements of 2 to the atoms. And so in a sense, transitions are labeled by X or by the discretized X. But they have a certain structure to them that's not apparent, not immediately apparent in the nerve. It is more immediately apparent if you think about cubes that have vertices corresponding to covering elements and their complements. Like I've drawn here, think about a point in this 3-dimensional space being high above the VW plane if it is inside U. Think about the mapping psi that we just considered. And so there is this Steinkohr-Stogrin result that embeds any simplicial complex, so in particular our nerve, upon one barycentric subdivision, embeds it in the standard cubical complex that you get from 0, 1 to AP by removing the origin. The origin and all cells, all subcubes that touch the origin. The map is not a piecewise linear map on cubes. So in a sense, right, this is telling us that the geometric realization of the nerve is a cubical complex. But we have to be careful and understand that, for example, here in the red triangle that we see inside the nerve, we can see 3 2-dimensional cubes, which are mapped non-linearly, but piecewise linearly into the appropriate 2-dimensional cubes in 0, 1 to the AP minus the origin. And so these vertices, so the vertices of the barycentric subdivision correspond to the elements of the nerve itself, correspond to the complete Boolean observations, that is vertices of the cube, that may show up as actual observations. But it also shows you that this cubical complex is homotopy equivalent to the nerve, which is an interesting which is an interesting observation in its own right, and turned out to be useful previously in other work that I did in learning. And so the challenges here are that not all vertices of the nerve will lie in psi of x. So not all vertices of cube U are actually realized in x. And so if you are interested in, if you're interested in elements of the discretization, right, vertices of cube U that are witnessed by points in the space, and seemingly we are, in case that we want to somehow match paths in X to right, paths in X to plans in this strange product, we need to understand whether this realized part of cube U, when this realized part of cube U, this will be our candidate for X prime. When is it a valid homotopy model for X? And then from there, we would construct an informative X prime product with the automaton in much the same way as we did before, because X prime could be thought of in terms of the different vertices and which controllers would move us between the different vertices of cube U. So this is what we're working on right now. We're looking to construct a few simple, nice examples and trying to ask, trying to get a construction that's meaningful and asking the questions, right, what can we say about the task space of all phees, of all formulae phi that are compatible, for which the task actually is executable, for which a plan can be constructed. Can somehow this compatibility be more easily characterized using the topological toolbox, homology groups, perhaps? What is the complexity of path planning in this space? Because this is where we're going to do path planning in some sense. Are there interesting extensions of things like TC to these kind of spaces? And so I'll now step away from high-level abstractions to talk a little bit about what kind of task you have to solve in a situation, in a complicated situation where such a high-level abstraction might be needed. So sort of going back from global to local, we meet another taste of what people mean in the robotics community when they talk about autonomy, and specifically in mobile agent systems. So the challenge that I propose is this. We would like to somehow, think of it as a grand challenge, so it's far away for today. But we would like eventually to be able to generate autonomously complex, distributed, cooperative behaviors which require reasoning over very large combinatorial structures. And for example, what do I mean by that? So in a network of mobile agents where perhaps communication is distance limited, you end up having to maintain communication graphs. And so imagine that you have perhaps at communication tree like this, and then the agents move a little bit, and as a result, this tree is no longer feasible, but perhaps a different tree works. And then using this tree, perhaps I would like to start moving. And so we move, and we encounter a situation in which there is an obstacle. We could circumnavigate the obstacle, but that perhaps is not acceptable in terms of cost. And so what you might do is plan to break the structure and reconnect on the other side. And then you can consider a similar situation, but perhaps some additional resources, additional agents join the game, making the circumnavigation of the obstacle a simpler task. Simpler, not in any formal sense right now, just intuitively. This picture seemed easier to deal with than the previous one because fewer disconnections were needed. And so here, the very large combinatorial structure from the challenge is the space of all spanning trees over a varying set of agents. So potentially an infinite set. You expect to seek some sort of categorical framework to serve as the skeleton, as the indexing skeleton to this problem. And so from here, it becomes clear that if a fundamental problem is how to maintain a fixed communication graph, but autonomy is supposed to mean that you do not assume that your obstacles are spheres. You do not assume too much about your domain, and you try to deal with it. And so it turned out a couple of years ago when I started working on this particular problem is that this problem is in some sense new. So you look at the mobile agent system with fully actuated dynamics, individual dynamics, and say in a compact domain omega that's sufficiently nice, but of general shape. And so you still have distance limited, you assume distant limited communications. You prescribe a communication graph. Of course, your initial position should be, your initial configuration should be, should allow for that communication graph. And now I would like to sort of introduce the problem. So let's read the task first. We would like the multi-agent system, for example, to follow a leader, a designated leader, while maintaining the communication graph that was initially designated to it. However, so it turned out that in the literature, there are many solutions of problems like this and even more complicated ones, but again, subject to the spherical cows assumption. Obstacles are spherical. And so really an obstacle is a center in a radius. Agents are spherical if you're adding collision constraints. And so it turned out that these solutions are not very easily, not very easily twisted, deformed into solutions that could accept complex obstacles. And so I started thinking, well, suppose one robot is capable of navigating this environment omega. Can we somehow prescribe a way by which it will navigate, by which automatically the network will know how to navigate omega? The kind of solution you're looking for is roughly this. So here's one option. And perhaps here's another example, which is a little bit more ambitious, because you might notice that the agents are only moving when they really, really have to. So this is the kind of behavior we're talking about. And perhaps a prettier, more up-to-date one. Let me get out of here for a second. And so this is for non-convex obstacles. And basically, and for more than one obstacle, which is why I wanted you to see this example. Basically, using a single agent state-of-the-art solution, you want to bootstrap a solution for the entire network that will keep the network connected. Now, there are obvious topological issues here, right? If say the network were the prescribed network were a closed cycle, and the agents were running around the obstacle, the leader was trying to run away from the obstacle, then we shouldn't have a result at all. And so let me return to the presentation. And so
there's a question posed for you in the chat, Dan.
Oh, I'm sorry, I cannot monitor the chat. Just a second. Does your topological constraint relate to the rigidity of your model or optimization of your model? The topological constraint here arises because I want to keep, I've made the rigid decision that a certain graph, communication graph, has to be preserved. And so if, for example, the communication graph is a cycle of agents around an obstacle, then since two agents that are joined together have to maintain a distance, a communication distance between them, or a distance less than no larger than the communication distance between them for all time, it will be impossible to move this essentially closed continuous loop, right, around the obstacle, to move it away from the obstacle to satisfy a leader that tries to go very, very far away. So this is where the topological constraints show up. In higher dimensions, it can be even more interesting, because you could imagine something like a drag net that gets stuck on obstacles. Did I answer the question? I'm sorry, I did not see a response. Oh, thank you. And so you can think about some objections from the engineering point of view. Well, let's think about one. So why restrict to fully actuated dynamics? And of course, you needn't do that, right? That is what quote unquote local autonomy is for. This is the simplest, highest level case for a controls person. And there will be a question of whether any sort of framework we come up with for the fully actuated case could be generalized to situations, say, with holonomic constraints. We are actually working now with a student on trying to realize our solution with differential drive, so with wheeled robots. Another objection is basically, well, if the agents are capable of communicating and the leader has information about where it is and can pass along information to the followers, why not share target information and then navigate individually? And the answer is that when you apply a navigation field, when you apply a state-of-the-art navigation field, this is what can happen. So if you let everyone navigate individually, then the connections are not going to be maintained in general. And the connections between agents in the network are not just for the sake of sharing information, they're perhaps for the sake of sharing information while executing another task in parallel. And so there is a reason why information is shared beyond the specification of the task, as we had specified it. And so, yes, this was a talk. This part of the talk is essentially a recycled conference presentation for American Controls Conference that we gave. And so there will be statements that this problem had already been solved many times. The answer being that yes, but only for convex domains, only for point spherical obstacles, so only under spherical Cauchy assumptions was it solved before. And what we are interested in is, again, in a prescriptive extension of any solution of perhaps of some particular kind, or prescriptive extension of a class of arbitrary single agent navigation solutions to a distributed graph maintaining mass controller. And so now let's talk about what does it mean to have a single agent navigation solution. And notice that this is far from the planning framework. So here we're basically going to the navigation field framework, but realizing that we would like to be able to navigate within omega. Knowing how to navigate within omega means knowing how to navigate to any target within omega. And so there is a little bit of similarity with the very, very first sentences in the definition of TC. You want a vector field, but essentially a parametric family of vector fields defined on omega. And then you recognize the other requirements. So first, you want the boundary of omega to be repelling. And then the second requirement is that the target y is the only stable equilibrium of the vector field you get by fixing the target y. And for almost all initial conditions, you would like this this ODE, right, to have trajectories converging to the target. And there is a technical condition that essentially says that if targets are close enough, and they don't have to be uniformly close, if targets are close enough, then the navigation field is not going to die on you. It's going to be comparable to the distance to the target. And so this removes the need for discussing omega. If you are provided magically a navigation field, you don't even need to know what omega is. And so this is consistent. Another thing is that this is consistent with a dual-Lyapunov type of condition that enables analyzing fields that are not only fields that are gradient fields of navigation functions. So there is a good compatibility with state-of-the-art tools for this definition. And so we think about configurations, or they're also known as ensemble states. We will not consider collision-free navigation in this case. I have not considered it, that this is perhaps something for future work. I find that there are many interesting questions about this situation, about this setting that are more important, more immediate. And so we can talk about the available edges, and given a distance s, we can talk about the edges that are available to the community, right? That is the community of robots I was talking about in the title. So we're looking at the edges available to the community. Out of those, we can talk about configurations that maintain a particular set of available edges. And so the problem we solved is we proved the weak invariance criterion for graph maintenance. Basically, given any, let's call it safe radius rho that's less than the communication radius r, you would like to construct a controller U such that every solution of x dot equals U with initial safe condition x naught in C rho G remains in CRG. So basically, if you start with a graph whose edges are no longer than rho, then you can keep those edges to be no longer than R. And so we have to finish soon. So I'll describe the proposed solution. So the idea is essentially to bootstrap the direct consensus dynamics on the system. We will have every agent P interact with its neighbors in the graph through the navigation field. So normally you would just have agent P take an average, a weighted average of the differences with its neighbors, of the relative positions to its neighbors. And then analyzing the graph Laplacian using the properties of Laplacians of connected graphs, one would come up with a conclusion that all the agents are being attracted to each other. And then if you perturb this vector field, this cooperative field, by a task component that's not too big, the result would be that the graph will be maintained. This is a result of Boskos and Dimaroganos in 2007, I think. And so instead of the radial interactions, I proposed to put the navigation field from P to Q, from me to my neighbors, and then superpose these fields with certain coefficients, psi PQ, with certain rescaling factors. And the point being that obstacle avoidance, no matter the shape of the obstacles, is baked in. It's baked in because each of these navigation fields pushes you away from obstacle boundaries. And so if you take a positive combination, non-negative combination of these navigation fields, you'll be pushed away from obstacle boundaries as well. But what might happen is that somehow, perhaps this may contribute to growing of distances. And so there is no clarity immediately that this sort of cooperation will do the job we want. The task component for our simulations was for the leader to just go to a target while removing all interactions, right? The other interactions with its neighbors. And so the leader essentially goes to the target regardless of what the community does, and the community needs to keep up. And so if these rescaling factors were identically 1, things seem to work in the complement of a circle or in the complement of a sphere. They seem to work nicely. There is a reason for it. But once you deform the obstacle, you will need to crank up the gain on the community interaction in order for the leader not to run away from the community or to not split the graph up in some other way. So slowing down the leader, of course, if you slow them down sufficiently, will work. And so the question is there a way for us to somehow analyze how much the leader should be slowed down? And it turns out that just with psi PQ being equal to 1, it's not an easy task. And the solution was to introduce a condition. So first, we would like to introduce some variable edge tension that stiffens. Think of spring interactions that stiffen if the distance between two agents grows beyond the safe radius. And then these asymmetric rescaling factors, just for you to see a formula, in reality, what they're for is to create the following effect. So we are going to ask for navigation fields. So this is a quality assumption on the kind of single agent know-how that we asked for. We're going to ask for the navigation field to be good, R delta good, where R is the communication radius. And basically that says that within a distance R from, say, from a target or from myself, the navigation field will never veer too far from the radius vector between the target and my current state. Right, we're bounding from below the cosine of the angle between the navigation field and the radius vector. And so you could, in principle, for smooth boundaries, you see that you could get better delta, right? Better delta for smaller r. And so there is a result that utilizes the projection of the navigation field to the radial component to create a connection and analyze a connection with a graph Laplacian with those stiff springs that I've written down here. And that's what produces this result. And the result is a little dissatisfactory because notice that there is this delta that we want to be close to 1. And so this parameter delta star needs to be closer to, right? Needs to be brought close to 0. But then notice that delta and delta star are not a property that we can fool around with. They're a property of the field that's fixed, of the vector field, the navigation field that's fixed. And so it is very hard to satisfy this constraint that delta star is so little that it is less than this number that changes as 1 over n to the 4th, right? Grows as 1 over, well, goes to 0 as 1 over n to the 4th as n goes to infinity. But suppose we've had the chance to do this, then there is also a gain gamma that slows down, right? The rate of slowing down of the leader that would guarantee that our graph is being maintained. And that again tells us that gamma has to be very small comparison to delta. And the surprising part is that in reality, the gains that we actually see in real life, so to speak, are better by 5 orders of magnitude than the gains that the theorem requires. So in fact, I have to report that this theorem shows very poor understanding of what's going on with this controller. So there is a lot more to learn. And so these are just pictures of what things look like when you have stiffer strings. Of course, stiffer springs, of course, the agents get compressed very fast, very quickly. And I think I'm already over time, so I will sort of stop here. These final thoughts are good for May, June of last year. So too much shrinking is going on. Can we minimize control effort in some sense? And yes, we have a result now that's under review that that says you can do this, in fact, but while improving the gain bounds. But perhaps more importantly, there is this lingering question about how do you address the topological constraints? How do you account for cycles winding around the obstacles and trapping them, perhaps in 2D, in 3D? There is, my next goal would be to formulate this sort of R course, R being the communication radius, R course homotopy/homology theory for this kind of problem, and try to connect it with questions about complexity of planning. So I think this is where I will stop. And I reiterate the call, if any one of you is interested in any problem that even remotely sounds like one of these, I would be very, very glad to talk to you and to try to understand what bothers you, and hopefully work together and gain more understanding into what autonomy really is. Thank you very much. I'll stop here.
Thank the speaker. Are there any questions for Dan?
Dan, I have a question about this fee that you use. Is it just, I think of the way you describe the planning, the alphabet and everything as just a bunch of ones and zeros, and the ones say you're in a certain region and the zeros say you're not. So is the fee just constraining which ones and zeros appear in that subset of the 2 to the alphabet?
Fee constrains, so it's a logical formula in the sense that you can write a word, right? A finite word that will constrain the set of all possible paths satisfying that word. So for example, I could ask to get, so say I'm on the circle and I have 4 points, A, B, C, D, and I could ask to, can I actually, let me see if I can try drawing. Just a second, whiteboard. Okay, let's see if this works. So say I'm on a circle and I would have regions, perhaps A is this interval and B is this interval. I would like to, well, I'd ask you to forget about what I told you about covers and things like that. So say these are the regions A, B, C, D. And so I could ask for, could ask to eventually, this is the symbol for eventually, right? So I would like to eventually reach A. No, I'm not going to try to write the formula down. I'll just write it in words. Reach A, right, from C while avoiding D. Right, and so we can see obviously that we should be going through B, but you could define infinite behaviors, and so you have this automaton. It has a state space Q, and every time you make an observation in the world in some state Q, that observation, so that's something, observation in 2 to the atomic propositions, that observation takes you to a state Q prime. Right, so in a sense, the automaton maintains a certain representation of what has happened so far, though it is a finite representation, right? Because there are finitely many states, and so the words that are accepted by the automaton are words that visit a subset of final states infinitely often. That is the definition of an accepting automaton, say, of words being accepted by an automaton of this kind. This is a Buki, known as a Buki automaton. And so perhaps it's better not to think of the formula so much as to think of Buki automata, because Buki automata are in fact a little bit more general than LTL formulae. Say LTL is linear temporal logic, one of the more standard logics to work with. And so what you would expect sort of from, in the topological setting is that you will get some sort of something like a covering space, right, of the circle that would encode moving along which, right, creating infinite paths in which will result in all the possible infinite words that the Buki automaton can accept.
Okay, that helps a little bit. Thanks.
You're welcome. Yeah, how to get a Buki automaton from a formula, that's an involved question, and there's still a lot of research going on about how to get the best Buki automata and so on from LTL formulae. This is by far not an open, not a closed set of problems, and trying to contribute by leveraging topology, I think, is important.
Okay, I'm going to stop the recording. If there are more questions, please feel free to pose them.